So in this video, we're going to talk about hypothesis testing. So what do we actually mean when we say hypothesis testing? So as researchers and investigators, we are interested in the validity of the results that we find from our experiments and surveys. So through hypothesis testing, we can say whether we are confident about the results or not. So in other words, we want to make sure that the results that we got were not by chance and that those results can actually be reproducible. So let's suppose if someone else carries out a similar experiment, they can come up with the same conclusions. So in order to fully grasp the idea of hypothesis testing, we have to look at a practical example to put theory into context. So let's suppose there's a classroom teacher who claims that the students in his classroom have an IQ which is above the average level of IQ in the population. So let's suppose we want to test this claim of having a higher IQ for the classroom through hypothesis testing. So we want to know a number of data points in order to test this hypothesis. So let's suppose this teacher actually selects 30 random students from his classroom and calculates their mean IQ scores, and those IQ scores come out to be 112. So mean IQ for class comes out to be 112. So remember that the total sample size in this case was 30. So beyond this piece of information, we also have to know the true population mean of IQ scores and also the standard deviation for the IQ scores in the population. So let's assume, for the sake of simplicity, that we know that in this case, and it is equal to 100. So the mean IQ for the population is equal to 100. And let's also assume that we know the standard deviation of the IQ scores for the population, and that is equal to 15. So given this piece of information, we want to test this hypothesis of a higher IQ level for the class. So the first thing which will come to your mind is that since this teacher actually took out a random sample of students, of 30 students, and actually calculated their mean IQ scores of 112, and we know that the population IQ score, the mean for the IQ scores for the total population is 100, why do we actually need to see that there is a difference or not? Because we actually see that there is a difference in the two means. So through hypothesis testing, you can actually be sure that there is a difference which exists for this classroom, and we did not actually make an error in calculation of the mean scores for the class IQ. So the next thing that we have to do is to figure out what will be our level of significance. So in this scenario, I'll go with the standard level of significance which is most commonly used, which is 5%, and we can denote this by 0.05. So what this 5% level of significance means is that if we actually reject the null hypothesis, we can be 95% sure that there's actually a difference between these two means. In other words, we can say that if we figure out that we are rejecting the null hypothesis, there's a 5% chance of making an error in concluding that the difference actually exists when it does not. So let's see how to figure out the rejection area on the bell curve. So to draw the bell curve for this given data, we need to center it around the mean for the population, which is equal to 100. So the next step that we're going to do is that we're going to write our null and alternative hypothesis. So the null hypothesis in our case would be, so this H naught is just the fancy way of writing the null hypothesis. It'll be mu is equal to 100. So this is the accepted fact. This is the population mean of IQ scores. So the alternative hypothesis in this case would be this claim made by the teacher that the mean IQ in his classroom is actually 112, which is greater than 100. So since this alternative hypothesis is that mu, or population mean, is greater than 100, we are only actually interested in this right hand side of the distribution, because this is the side of the distribution where mu is actually greater than 100. So the next step is to figure out the area of rejection, and that area of rejection is the 5% area, the 5% of the total area under bell curve on the right hand side of the bell curve. Why is this the case? It is because our level of significance for this hypothesis testing is 5%. So if we actually calculate a z value which falls within this area over here, then we can reject the null hypothesis of mu equals to 100. Otherwise, we will fail to reject the null hypothesis. So in order to figure out if our calculated z-score falls within this area, we also have to find out what this critical z-score over here is at the boundary of this 5% level of significance. And we can actually find out this critical z-score by looking at the z-table. If you want more help in how to look at the z-table, you can access more videos from the Graduate Resource Center which talk about how to actually read the z-table. But I'm going to tell you what the critical z-score for the 5% level of significance for this one-tailed test is, and that is equal to 1.645. So the next step is to actually calculate the z-score given this piece of information over here, so that we can figure out if that z-score falls within this area or if it is less than 1.645. So let's actually calculate the z-score by this formula of x bar, which is the sample mean, minus mu, which is the population mean, divided by the standard deviation of the population over the square root of the sample size. So just plugging in the numbers, we have 112 as x bar, 100 as mu, 15 as the standard deviation of the population, and our sample size is 30. So this actually, if we calculate all these, if we put all these numbers in the calculator, we will get 4.32 as our z-score. So let's compare this z-score to the critical z-score. So we can easily see that the z-score is way greater than the critical z-score, which means that it actually lies somewhere in this region, which means that this number lies in the area of rejection, which ultimately means that we can reject the null hypothesis that mu is equal to 100. And through hypothesis testing, we can actually say that the mean IQ for this class is greater than 100. So let's think about this for a second over here. So what we were dealing with over here was a one-tailed hypothesis testing. So what if the teacher actually claimed that the mean IQ for his class is not equal to the mean IQ of the total population? In that case, we would be using a two-tailed hypothesis testing. So in the case of a two-tailed hypothesis testing, what we're going to do is that we're going to divide this level of significance of 5% into two areas on both ends of the normal distribution into areas of 2.5% each, 5% or 0.025. So similarly, on the right end of this distribution, the area of rejection will comprise of 2.5% of the total area, or 0.025. So another thing which will be different for the case of two-tailed hypothesis testing is that our alternative hypothesis would change to mu is not equal to 100 rather than mu is greater than 100, like in the case of one-tailed hypothesis testing. So we need to figure out the critical values, the critical z-scores for these boundaries for the 2.5% level of significance at both ends, and I'm going to tell you these, and you can also learn how to look at the z-table and calculate these yourselves. These will be equal to minus 1.96 on the left hand side and 1.96 on the right hand side. So our area of rejection then becomes, if your z-score is less than minus 1.96 or greater than 1.96, then it falls in the area of rejection, and you can reject the null hypothesis. Otherwise, you will fail to reject the null hypothesis. So we have already calculated the z-score given the information that we had. The z-score is not going to change. The z-score will remain the same whether it's a two-tailed or a one-tailed test. So the z-score remains the same, which is 4.32, and we can easily see that this 4.32 falls in this area over here, right of 1.96, which is one of the two areas of rejection in this case of two-tailed hypothesis testing. So we can basically go on and reject the null hypothesis for this two-tailed hypothesis testing case too. So we can say that the null hypothesis of mu equals to 100 is rejected, and the mean IQ for the class is actually different than 100.